we are going to cover an introduction to using Tableau's geographic and geometry types for plotting data. For the most part, at small resolution, actually, let's step back a bit. So this is about visualizing points, lines, and areas, which are called polygons. Polygons on maps. So that's the whole point of Tableau's geographic system. I think we actually taken we haven't done much work into this. At small scales, when we take a small tiny patch of the Earth, this works out to be a pretty traditional XY plane with latitude in the y-axis and longitude in the x-axis. Where this falls apart is when you start looking at bigger and bigger areas. We actually end up, looking at the entire surface of the Earth, which is not flat; it's on a sphere. So, technically, Tableau uses this is the Mercator projection. Yes. So Tableau uses what's called a Mercator projection, which has a number of strong limitations. The biggest of which is that it turns a single point at the North Pole and a single point at the South Pole into an entire line. So there is at large scales, there's a significant amount of distortion, and we will look at that distortion. Actually, we'll play around with just putting some points on a map and looking at how it distorts lines and distorts circles, and how points move through the plates. So Tableau uses the Mercator projection to create flat maps. This causes large distortions and discontinuities at the poles. Discontinuities at the poles. So what it means is if we draw a little circle of like 300 nautical miles here, it'll just look like a little circle. If we move it all the way up here, it's going to take up like most of the pole. And like once you're at the pole itself, 300 nautical miles will be, let me think of this, 5 degrees. 600 nautical miles is 10 degrees. Quick fact, 1 nautical mile is 1/60th of a degree. So 600 nautical miles is 10 degrees, 300 nautical miles is 5 degrees. So it'd just be a straight line. So the same area, no matter where you put it on Earth, right? It's this little circle, 300 nautical miles apart. But when projected onto the actual screen in Tableau, will look like a circle at the equator, but will become a box at the pole. And this is important to know because when you're trying to fairly represent particularly geographic data with polygons and areas and lines, you need to be aware of this distortion and the fact that this distortion can if you're, for example, using polygons to represent areas that represent some sort of important fairness metric, it can, of course, distort. It can, of course, make things look like much bigger at the poles. So, how to visualize a Mercator projection. We imagine the Earth, surround it by a cylinder, and then what happens is we project the poles, we project the equator out to the middle of the cylinder, right? Just like this, like that, and then the poles, the points near the poles, so we have points like this, they get mapped out to here, right? So this point goes to here, this point goes to here, so on, like that. Mercator projection just, and the problem is, as you take this process up to the pole, all of a sudden, all the points at the North Pole point to everything going around a circle. And so the whole North Pole becomes a line, and the whole South Pole becomes a line. So it's just an important caveat to understand about the Mercator projection, is that it causes extreme distortions at the poles. Now, Tableau uses the longitude-latitude coordinate system. They don't use east and west. Oh yeah, we've already looked at this because of the hurricane data. They don't use, they don't say like degrees east or degrees west. What they do is they reference the UTC line going through Greenwich, England. And so 0 degrees is UTC through Greenwich. Again, because the bloody British sailed the whole world, they got to choose where they put the center of the world. The cheeky Brits, right? A joke on the rest of us. So the way Tableau's coordinate system works is positive values all the way out to 180 degrees, travel eastward. Negative values out to a negative 180 degrees, travel westward. But what we're going to do is we're going to play with those values and show that they're willing to, we're allowed to put in latitudes bigger than 180 degrees. We can go all the way, we can put in 3 times 8 is 24. We can put in 1040, right? 1040 is 3 loops, right? So I can put in 1040 and we'll watch our point loop 3 times around the globe. And the same thing, if I go minus 1040, we can watch our point go 3 times around the globe, heading westwards. Now, on the vertical axis, Tableau doesn't use north or south, it uses positive and negative. And so we have 0 degrees is the equator, plus 90 degrees is the North Pole, and minus 90 degrees is the South Pole. And it, again, Tableau will loop these over. So if it goes to 97 degrees, then it goes to the North Pole and then goes back down the other side by 7 degrees. So what we'll do is we'll move a point to, say, 25 degrees of longitude, and we'll move it north 80, 90, and then we'll do it 95, and we'll see it pop out the other side, right? Or at least it should, if they're being mathematically correct. And we're going to do that just with parameter controls. And the idea of today's exercises in class is to build up your intuition about how Tableau is geometrically plotting these map points, so that when you go to work with actual data sets with map points in them, you understand why it's sometimes doing weird things. And we'll get to do other fun things, like Tableau's plotting of lines doesn't plot straight lines across the graph. The Tableau's line plotting algorithm actually plots the great circle lines. It plots the geodesics, what you would expect for a flight line from, say, Paris to New York. You'd expect a curved line Calgary to London, or Gatwick, takes a line that actually crosses right over top of Iceland, parts of the Greenland ice sheet, Baffin Bay, and then comes down. I'm sure some of you have probably actually flown that flight I have as well. And it's quite something to be like flying over Iceland and looking down on its waterfalls and stuff. Wow, holy smokes. We're quite far north. So any questions about Tableau's, Tableau, the coordinate access that Tableau uses for, and again, these are your rows, and these are your columns. This is also the x-axis, and this is also the y-axis. Any questions so far about how Tableau, sort of the engine and dynamics behind the scenes of how Tableau is going to plot your geographic points? The only good part of the Mercator projection is things in the middle latitudes, when zoomed in close enough, look flat, right? That's the only thing, so that you can zoom in, and if you're working with things in the mid latitudes, it looks flat. Things fall apart when you try to zoom in on these maps in the extremes of the poles. They just you have to zoom in quite a lot, like down to like 1 or 2 kilometers, or even smaller than that, to actually get a proper flat projection. So to get started, we're going to create some parameters, right? That will allow us to play with points. And we're going to create parameters for latitude and longitude, and we're going to give them reasonable ranges. And then we're going to start creating points from those parameter values. So the first thing I'm going to do is I'm going to create a latitude called start latitude for a start point. So I'm going to create a parameter. I'm going to call it my start latitude. And for now, I'm not going to wrap it around the globe multiple times. This is just going to be a start point, and I'm going to create it as an integer. That's fine. I want it to be a range, and I want it to be from the South Pole, which is -90, to the North Pole, a maximum of +90, and we're done. That's it. Yeah.
So,
Yeah.
The bearing from Teams.
Oh, we'll get that's if I can get time to look at it. Don't worry about the bearing file yet. Again, if you look at the note on Teams, I said if we can get time to look at this. I want to cover the absolute basics first, and the absolute basics is just having some points we can play with, right? Without having to worry about extra data. And I will show you how to do the data densification trick, how to basically link two tables together on nothing at all, so that you get. Did you guys cover full joins in SQL, where you take rows and rows and you multiply them together? Yeah. So Tableau can do that as well. So I'm just creating a start latitude. It goes from +90 to -90 in steps of 1, so 1 degree at a time, which sounds great. I'm going to do the same thing for a start longitude. Create parameter. And I'm just going to go from start longitude. And I'm going to make that an integer as well. And again, I'm going to make it a range from the range will be from -180. -180 and +180 are the same point, opposite Greenwich, right? So I'm going to make it go from -180, positive values, so it's going to rotate eastwards, go through Greenwich, or go through UTC, and then head eastwards and all the way back to the starting again. So we do -180, which is somewhere in the Pacific, just the west of Hawaii, to +180, step size is 1. We say, okay. So we've got 2 points. Let's make a point. And it's as simple as creating a calculated field. I can just say start point. Done like that. And I say make point, two numbers. Start latitude, comma, start longitude. Okay. Now, when I drag this over and just drop it here, it's going to create a generated latitude and longitude in the rows and columns, and it's going to wrap this in something called the collect function. And the collect function is Tableau's, it's Tableau's version of an aggregate, but for geometric data. So, and this is an important thing. So, the collect function is an aggregator of one or more rows of geometry. So lines, point of geometries. So in particular, we will see later on that collect can be used to create polygons or either paths or polygons, either one of them, from multiple rows of positions. So we've got a point here. Let's try to control where it's sitting at. So we're going to show the parameter control, so that's our latitude, and show our parameter control. So we're going to start latitude of 1 degree. I can set this to 0, and let's set this to UTC 0 again. So there we are. We're out in the middle of the ocean, and what I can do is I can zoom this out a little bit, and you can see that this little pin icon comes on. It means that the axis ranges aren't going to change no matter how much I move things around. So let's move this start point around a little bit. I'm going to move it eastwards, right? So it moves eastwards as expected. I can move it south, right? Moving it south, moving it all the way to the pole, and you can see it disappears right at 90 degrees. And I'm just going to save this to save the progress so far. So we can move this northwards as well. So that's no big surprises there, I don't think, that we can move a point around. So if we can move it, I'm going to try to roughly get it over top of, line it up. Oh, you know what, we can try to get it to Calgary-ish. 50, yeah, I think we're about 50. And I'm going to go longitude. There we go. Close enough. We can do longitude 120. And we'll just set this right at 50. There we go. So that's a start point. And you know, nothing too adventurous about that. When you have collect, if you do collect on one of the columns in your data set, for every, and you do it just as map point, for every point latitude and longitude, every point in your collection, it'll actually plot a single point. And later on, I'll show you that if you change the data type from map to polygon, it can create a whole polygon, like a filled area, from a set of points. So that's pretty handy if you have a data set whose rows each contain one point, so if you have a data set, for example, of a circuit that's been traveled by a delivery truck, you can, and it comes back to its starting point eventually. You can use the waypoints to create a filled area inside of here. There is a nuance to this, which is this is a filled area sitting on a globe. So it's actually not super well defined, right? If you've got a closed path on a globe, does that closed path enclose the bigger area outside of that path, or does it enclose the little area? Mathematically, if they were doing to do it mathematically correctly, they would use something called the right-hand rule, which is depending on the ordering of your points, you would determine whether you color the inside or the outside. The way Tableau has chosen to do it is with a simple if statement. If the area is smaller, color the smaller area. So you're never actually able to color areas that are bigger and on the outside. I tried, I spent the whole weekend trying to trick Tableau into coloring bigger areas. It is very hard to do. Tableau just has this really simple if statement behind the scenes, and it looks at the two areas, the area outside your path and the area inside of your path, and it just says color the smaller area, and it always does that no matter what. And we can actually demonstrate that using their buffer. So let's go ahead and put in a stop point, and then we can use our stop latitude and stop longitude to move that stop point to approximately Gatwick. Yeah.
For the parameter, that was the start latitude.
Yeah.
The step size was
One.
minus.
Just 1 degree of latitude at a time.
No, I mean for the parameter, not the generated. The step size was okay. It was 1.
Yeah.
But it was minus 180 degrees and 180.
For the longitude, yes.
And what about for the latitude?
Latitude, so this is minus 90, and this is plus 90.
Okay.
This is, these 2 points are actually the same point on the planet. Minus 180 over here and plus 180 here are actually, well, technically you can see the map ends here. So minus 180 and plus 180 are the same point on the planet.
What is the start point?
The 0 longitude, this is 0 longitude here, going right through Greenwich, England, right? Going through West Africa.
Here in our parameter, here, what is the start point?
What are these? Oh, what is that start point?
Yes.
It's a function, it's a calculated field that uses one single. The start point uses just a single Tableau calculation.
Okay, position, it is showing the position.
Yeah, it's technically what it's doing is it's creating what's called a geometry, and that's a specialized bit of binary data behind the scenes that represents a position on the planet.
So can I just see the formula for the calculated for the generated longitude?
Oh, all I did was just drag it onto the. To the thing. So if I take all of these away and just leave, I'm just going to take all of this away. So I have the start point, right? We saw that was. Let's just make a point. I'm just going to drag it into the middle, and it just shows up, just like that. And here we can see that I've got the longitude wrong, right? So I can move the longitude. That's not quite right. A few more provinces over. Oh, and you can see a sploochy bit of gray up there. That's approximately Calgary. There we go. 51 degrees north, 14 degrees west. It is, approximately Calgary. So I can zoom out, zoom out, zoom out, zoom out. There we go, and zoom out again. Now you can see that it recentered. It automatically recentered around Calgary, which I understand what the developers are trying to get at, right? They're trying to make it as automatically friendly as possible. But the downside of that is that sometimes you don't want it centered on where your point is. You want it centered on some other thing. But you know what? We've put it on Calgary. We'll work with that for now. So let's do the same steps again. We'll create another parameter called stop latitude. And it looks to be good. Say okay. And we're gonna create another parameter called stop longitude. And that looks okay, min max, values, yes. Okay. And now let's create a stop point. Field, stop point. And we're going to do the exact same thing. We're just going to make a point. And I'm going to drop the latitude in. Stop latitude. Tab. Stop. Oh, did I not spell that correctly?
Yeah.
No.
No, I spelled it incorrectly. I have to just fix the spelling error there. Okay, so I'm just going to go and fix the spelling error. Edit. Now what I'm going to do is, remember I promised that we can wrap these around multiple times. I'm going to set this up to 1040, which is 3 times 360. Is that right? 3900 plus 240. That should be right. And I'm going to allow this to wrap. Let's see how many. You know what? I will allow this to wrap. I'll set these both to show both boundary controls. And I'm just going to allow the latitude to wrap as well a bunch of times so we can see what it does when it wraps. So I'm going to set this to 360 and 360. Okay. So we've got the stop latitude and start latitude. Now the question is, in this form, I've got, so collect works with just one field. You can only put one field in here. I can't put start and stop into collect. So the question is, how do you get 2 geometries to display, right? And they can be different geometries. One thing could be polygons, another one could be a path. One could be points, and the other could be polygons. You know, you have some flexibility. The caveat is you can only get at most 2 different geometries on here. You can't get 3 or 4 or 10. There's no way to use the measure values field to get multiple geometries on there. I've tried. It won't do that. So the way you do this is you take your generated longitude, slide it over, and create 2 maps. And now you can see I've got 2 copies of the same field. And all I'm going to do is I'm going to replace the start with the stop point, just like this. And maybe I'll change this to a red, and I'll change this to a green for go. There we go. And finally, we use the dual axis trick. Here we go. We've got our 2 points. And what I can do is I can use the zoom area tool to adjust the stop longitude. So I'm going to move it to approximately, that looks about right. And actually, Gatwick is actually around 52 degrees. So there we go. I'm going to zoom back out again now that I've got those set up. So there we go. Now we've got a start and a stop point. But remember, I promised that I would show you wrapping these things around the world. And I'm just going to double check. I feel like I didn't calculate that correctly. 3 times 360. 1080. That's right, not 1040. So I'm just going to correct that bit of math. And also so I'm going to take the time to save my work. One of the caveats when working with this is that there is an undiagnosed buffer overflow. What's a buffer overflow? Basically means a calculation exceeded the amount of memory it's allowed to do. That happens in certain circumstances when you try to move some polygons to the far north. And again, remember I said that this is a big discontinuity at the poles because it's taking a point and turning it into a line, which is kind of like an act of going to infinity. So there's a bug in one of their implementations of one of their calculations, and it will spontaneously crash the program under very specific circumstances when you're moving points to the north. But we should be generally safe working with this. So I'm gonna edit this. That one's fine, cancel. I just need to set this to 1080. Set this to 1080.
So do we, how do we decide the range?
Generally, you're safe with between minus 180 and plus 180 for the points. So, and this is going to be true when you're doing your data coercion. Like, suppose you're being given like some data sets of like waypoints for a delivery truck, waypoints for a garbage truck, taxi waypoints, Uber waypoints. Right? You've got some data set of waypoints. Well, what you do is you make sure the value because you're working with circles, you can use modular arithmetic to ensure that the values are between minus 180 and plus 180 for the longitude, and plus 90 degrees and minus 90 degrees for the latitude. And you just use modular arithmetic to say, if you've gone past 90 degrees north, then you're going back south again, right? So you're doing a little bit of wraparound. But Tableau actually obliges us really nicely, and we'll do the wraparound ourselves. So let's do a little bit of wraparound work here. So I'm moving it. I'll move it out to, let's get it close to the edge here. 260 is too far. So you can see it's going around the side of the Earth, 178 degrees, and now it's shown up on the other side. So what's going on here? Again, 0 degrees is here. They put the boundary at 178 degrees. So 2 degrees past 178 degrees is 180 degrees, and you've already wrapped around the world. And as you add values, as we keep adding values, so this has to go, so when this hits 180 degrees, this has to be roughly, the middle of the Pacific. And as we keep adding values, we keep moving west. So adding positive values moves us west, right? So we're moving further, moves us east. Adding positive values moves us east. And you can see we're wrapping around. We're now 202 degrees to the east of UTC. We wrap back around again, and I can keep wrapping around. Just do this nice and fast, so you can see that even though the values keep getting larger and larger, they just wrap back around, right? And we can of course orbit around the planet 3 times because we've set this to 1080, so we're going to go the equator, UTC plus 1080 should bring us right back to the beginning, right? So that's where we started. So I'm going to set this back to close to 0 again. Increase this, there we go, 0, right? Now let's see what happens to the latitude when we move it north.
Is there a purpose for us that we are moving around here 3 times?
The purpose of this is to demonstrate that Tableau takes that longitude coordinate and does that wrapping calculation for you automatically.
Okay.
Right? So if someone gives you a data set and for whatever reason, so where you would see data sets with the possibility of values that exceed 180 and minus 180 is data sets that come from systems that do something called inertial navigation, where you have a direction and a distance, and maybe like an aircraft can have a direction and a distance, and that distance can be greater than half the circumference of the Earth, right? In which case it's wrapped around, right? And so you can end up, and especially if you have an aircraft that's made like multiple waypoints, right? You can end up with a net change in latitude that is greater than 360 degrees, right? So the example would be, if you have an aircraft that's flown from airport to airport, but done it 3 times, but gone around the world 3 times, doing stops at airports, and you've got the waypoints at the airports that it stopped at, then the net change in latitude would be 1080, right? The net change in longitude would be 1080 because it's flown around the Earth 3 times. And so in your data set, it might actually say 1080, right? And Tableau will happily actually plot that to the correct point for us. So I'm going to set the latitude at, the longitude at 25 degrees. And hopefully that's big enough that it will, so this is, 30 degrees. So I'll set it at 30 degrees. And if I'm heading north at 30 degrees, and I don't stop, I'm going to go right to the North Pole, and I'm going to come back out the other side of the planet, which would be at minus 150 degrees, right? Because I'm at plus 30 degrees, I'm going to come out at minus 150 degrees. So if I come out at negative 150 degrees, I should see this dot go up and then come down somewhere in here. And let's actually verify that this happens. Sometimes Tableau does not get it right. So, but let's see if they do. So we're going to go up, we're moving up, we're almost at the North Pole, we're at 90 degrees, 86, 87, 89. Please don't crash. 1 null. And, oh, no, Tableau does not like latitude. Tableau won't do circular arithmetic on, modular arithmetic on latitude. Okay, so now we know. We have to keep latitude minus 90 to plus 90. So I'll just fix that. And now we know. And remember I said in the regular expression class, try it out. If in doubt, try it out. Well, we tried it out. And now we know that Tableau only does modular arithmetic on longitude, not on latitude. So buyer beware. And I had this at 51. Or 52. And longitude I had at 0. So Tableau will do modular arithmetic for changes in longitude. It will not do it for changes in latitude. So it's DIY, for if you're doing what's called azimuth-bearing calculations for lines that go through the pole, we're going to have to figure it out ourselves. What that really means for your work day to day is when you're preparing data to be ingested into Tableau, like in Python or SQL, just make sure all your data points stay in a reasonable latitude range, right? They stay within sort of the tropics, right? The tropics of Capricorn. Or at least, actually, they stay below the Arctic and the Antarctic circles. They stay within the mid-zone. If you're working with data that's reasonably bounded within those zones, which is where most people live anyways, you don't have to worry about things wrapping over top of the North Pole. So the next thing I want to demonstrate is, let's connect this by the line that an airplane would fly if it went in a perfectly straight line, and that's called the great circle. Right? So what are great circle lines? Let's put a great circle line. A great circle line occurs if you take the Earth and you divide it with a plane, and the circle that divides that plane this is called the great circle. Great circle. And it's also called the geodesic path. Geodesic path. It is the geodesic path is the shortest point between, the shortest line between 2 points, for any 2 points on the planet. In our highways in North America, to stay on, to have a highway follow a fixed latitude, like to follow a latitude that way, what they do is they start on a bearing, like heading due west, but that ends up creeping north. So they have to curve the road back down again. They take it, it creeps north. And so like our highways going across Saskatchewan and Manitoba do these like dog legs, these sawtooth back and forth to end up in a straight, to end up following a single latitude. So let's make a geodesic between our 2 points. So we create a calculated field.
What do we call it, sir? This plane?
I'll write it here. I'm going to call it geodesic.
So this will be the shortest path
Yeah.
between 2 points.
Yeah, path. And we'll say, and all we have to do is we say make a line. And again, we need 2 things. We need a start, so we specify our start latitude, our start point, and our end, which is our stop point. Now, you can make this into one calculation. You could say make line, and then make point, comma, make point, and then put all the values in. I broke it out this way so that you guys could see how the individual calculated fields are put together. So I say, okay. Now, what I'm going to do is I'm going to get rid of our stop point because I'm going to replace it with the geodesic path. So I'm going to drag this over, drop it in, and now we have the shortest path. That is the shortest path between Gatwick and Calgary. Now what we can do is we can keep the longitude difference, right? Remember this longitude is at -114 and this longitude is at zero. And let's make the latitude closer to the pole, closer to the equator, and see what happens. And so it looks really tilted and weird, and there we go. That's just a straight line. And the reason why that's a straight line is because the equator is the only line of latitude that is also a great circle, right? Because you can see the distance along the latitude is the entire circumference of the Earth. Other latitudes, right? These latitudes are not great circles. Well, yeah, yeah. If we
is the biggest circle, I guess.
yeah, so yeah, so sorry, there's one more thing. The plane has to go, I didn't draw the plane correctly. The plane actually has to be going through. It's a plane you tilt through the center of the Earth. So I didn't draw this entirely accurately.
Kind of diagonal.
Yeah, it has to, the plane has to actually be more like this.
This is the plane.
Yeah, come on. And it has to actually be going through the center of the Earth. And that gives you your...
So why the second part is not equal to the end?
Why is it not shown? Because I can only put 2 geometries on I can only put a pair of geometries on here at a time, which like it can be quite limiting, right? Because I can't put like an end circle and a start circle. Now, if my data set was broken up so that for every path I had 2 rows, then I could collect on those rows and end up with 2 points, and then also tell it to draw a line between those 2 rows. And I'll actually demonstrate something similar to that. But the main point that I wanted to demonstrate was that the line that gets drawn is a great circle, and one of the things we can do again is to I can make my start and end latitudes the same, and or start and end longitudes the same. There we go. And we just end up with a straight line. And I can increase this latitude, I can decrease this latitude, and increase this latitude until we have just a single line going through the whole planet. And then we can modify the longitudes to see how things curve in strange paths here. So let's put this there. There we go. So, that longitude is, that's fine. I'm gonna edit that longitude. That's fine. So I'll set this to, I can try setting this to 100. See what happens if I do, 0 and 180 degrees are opposite each other. So, yeah, so 0 and 180, yeah, that's right. That's interesting. Yeah, so it can get a little counterintuitive at times. Now, so any questions about using the make line function to create a line geometry? You can use that on, like, it doesn't have to be parameters, right? You can use that on any 4 fields that have latitudes and longitudes associated with them, right? So any pair of latitudes, any pair of longitudes you can use to make lines, and the lines will be the geodesics. The lines will be geodesics of the planet. So the next thing that we're going to do is we're going to make a nighttime map, and we're going to demonstrate the Tableau. We're going to demonstrate Tableau's buffer to illustrate a nighttime, to illustrate where nighttime is on the planet. So what is Tableau's buffer? Well, Tableau's buffer takes a point and a radius, and I'm going to create a parameter, and this is going to be what I want to call this. This is like 1/4 of the circumference of the Earth, right? So this is going to be a constant parameter called I'm going to call it quarter circumference.
I guess E, there will be one more E, circumference, after F.
Yes, there it is, thank you. I'm going to make it an integer, and I'm going to make it just a single value. And that single value is going to be 5400. It's like 21600, divided by 2 is 1008, divided by 2 is 504. So this is when you have like magic values in there in Tableau, like the number of minutes in a day, right? You can type that out into your calculated field. I could type out 5400 into the buffer calculation, and it would just be like this magic value sitting there, like, what does that mean? So like in programming, where we create constants to sort of give a context to the magic value, we can create lists in Tableau, parameter lists that just have one value. I can't change the value of that because it's just one single value, is 5400. And we're going to use that to create a buffer around the planet, or around a point. So we'll just take our start point as our point, and we're going to create a calculated field. And all we have to do is we're going to say we're just going to say buffer, and we have to supply one or more points, If you supply multiple points, it tries to make a buffer around the line of those points. If you have a polygon, it'll make a buffer around the polygon. So what is a buffer? It's the area around the smooth. It's basically the smoothed area around a geometry. For a single point, it's just the circle of radius, buffer radius. So, oh, and that's, do I have it in there? Oh yes, I have nautical mile in meters. Okay, so I want to take my start point as where I want the point to be. I want my number to be the quarter radius, quarter circumference, and I need to edit that to say nautical miles, divided by, times how big a nautical mile is in meters, nautical miles in meters. And then I'm going to say my units of measurement for my buffer is in meters. Allowed units of measurement are meters, kilometers, miles, feet, I think. So I think Tableau being an American company, they have a heavy emphasis on imperial units of measure, but they do accept the standard SI measures as well of distance. So the first bit is, in this case, it's a point. It's a single point that we're going to be drawing a circle around. The second bit is how big we want that circle to be. So in this case, I want it to be as big as 1/4 of the Earth's circumference. And then I have to say, I know that in nautical miles, and I have to translate that into meters. So I multiply by the number of meters in a nautical mile.
What is the distance of nautical mile? Which distance it is?
I'll show you. Sorry, and I want to increase this. I want to call this nighttime.
So will this convert the nautical miles into meters?
This multiplying by this magic constant I put in here, which I'll show you right now. Okay, and so nautical miles is, well, first off, I can only select one value. I'm going to edit the parameter control. It's just a single value. It's 1,852. So it's the number of meters in a single nautical mile. It's almost a definition. The Earth gets bigger or smaller, so there's some variation in that. But basically, it's 1,852, and that's why I have the units in brackets there. A nautical mile in units of meters.
For circumference, we are using meters or kilometers?
We're using nautical miles because, let me get to the quarter circumference, edit. I'm going to call this nautical miles, NI, and it's 5,400. And that is because a nautical mile is by definition 1/60th of a degree, right? So, so all we have to do is take 90, right? A quarter of a circumference is 90 degrees, and multiply it by 60. And 6 times 9 is 54, so we get 5,400. And it's the reason why I've been using nautical miles is simply because there's that fixed relationship between what a nautical mile is defined as and the degrees in latitude and the degrees around the equator. So I've got this buffer here, and I'm just going to drop it. I'm just going to drop my nighttime buffer on here like this, and I'm going to zoom out. And it did not. Why did it not show? I need to show the parameter control. I'm going to set this to 0. And I'm going to set this to where's my longitude start. Oh, that's my longitude. I want to show my latitude. This up here, and let's set it to right at the equator. There we go. All right. Yes. That works perfectly. So, whoa.
Can you
That is-
explain again why nautical miles are 5400?
Oh, why the? So here's. There are 90 degrees in a quarter of a circle. Right, so if we have a circle,
Yeah.
draw it into quarters. This is 90 degrees, right? Then there are 60 nautical miles in a degree. And that's simply at the equator, at equator.
So this is a distance or something like?
Yes, and nautical miles is actually a distance as well, because it's relative to the total circumference of the Earth. So this amount is 90 degrees times 60 nautical miles equals 5400 nautical miles at the equator. Now the question is, why? Oh yeah, so what's going on here is this map illustrates where night and day would be at the equinoxes, right? At exactly the point where the tilt of Earth's axis, so the Earth is spinning this way, the tilt of Earth's axis is neither pointing towards the sun or away from the sun. It's perfectly like this or like this. So this is what night and day would look like on the equinoxes, and I can by changing the longitude, I can move night around, right? So I'm moving night over towards Calgary. So there's night overlapping us. There's night. Oh, yes, it broke. So yeah, Tableau does have these random. It does kind of randomly fall out. Fortunately, I have this open. Yes, it's still saved. Okay, I'm going to save this. Overwrite, save. Yes. So that's what it would look like at the equinoxes. Now, what about at the? What about when we're at the solstice, the winter solstice? Well, when we're at the winter solstice, the Earth's north pole is pointing 23 degrees away from the 23 degrees away from the sun, which means that the center of the dark spot is going to be at plus 23 degrees latitude. Okay, there we go. And I'm just going to adjust the color. I'm going to make it black, but then I'm going to make it like, yeah, let's do 25% shaded, right? So we get a sense of. So on December 21st, this is going to be the shape of nighttime on planet Earth. So, and again, we can move nighttime around, and slide it around. Like that. Just keep sliding things around. And do I have I'm just seeing if I have, I have a bearing distance, good. The distance along the bearing. So, let's see how we do time. Oh, I'm good, I can do that. So with this simple display, you know, eventually you could like you could do fancier calculations to tie this to the time of day, and you could actually have a slider for time, arbitrary time, and then just do a little bit of trigonometry with time to figure out these calculations. But for now, I just wanted to do it as simply as possible and just show how a buffer can color a whole region of the planet by using a very, very big radius. So the next question is, you know, that's a buffer of a fixed size. What do like smaller circles around points look like, right? Instead of these big ones. So let's create another one called, instead of nighttime, we'll just I'll call it circle distortion. I'm going to create a calculated field called circle distortion, and it's going to be another buffer, and I'm going to use the stop point this time, and I'm going to use a field called bearing distance, and I'll bring that up so that you guys can take a look at it, times nautical miles, and then just say that's units of meters. All right. So I'm gonna have to save this really quickly so I can show you what bearing distance is. So I'm gonna edit this. Bearing distance is simply an integer. Oh, yeah. Current value, yes. So bearing distance right now is an integer between 0 and 10,800. 10,800 seems like a magic number to pull out of nowhere. 10,800 is 180 times 60, and that's all it is. It's 180 times 60, so it's half of the circumference of the Earth. So all I'm saying is that we can make a buffer that takes up the whole planet, right? So if the middle of the buffer if the radius at the middle from the middle of the buffer is half the circumference of the Earth, then both sides of it will meet back again, and we'll have a buffer that fills the whole Earth. I'm going to set the current value to something nice and small, like I'll do 1 degree right now. I'll do 60 degrees latitude and say OK. And I'm just going to show the parameter control for start and stop. For stop, rather. Stop latitude, show parameter control. Stop longitude, show the parameter control. And I'll call this rename buffer distortion. And I'm just going to take my circle distortion and drop it on here. And I'm going to move it out of the north. And let's zoom out for a second so we can see where we are. So we're sitting off the coast of Africa. And and then what I'm going to do is I'm going to show the parameter control for the bearing distance. So I'm going to show the parameter control. And so I can start making this larger. I'll have to zoom out.
What is the formula for circle distortion?
Oh, yes, circle distortion is just a buffer calculation. Yeah. Right. So it's just any point and a distance, and then the units that those distances are in. And so what happens is I can make this bigger. Let's zoom the map out again. So that's zoomed out maximally. And as I make this, I'm going to save this real quick.
The distance is kind of radius of that circle. Or?
That's exactly what it is. But look at what's happening to the circle. It's distorting. It's not a circle on the map anymore. And this distortion is due to the fact, and now it's not even a circle. This distortion is due to the fact of the Mercator projection. So what we've got here is we've still got a circle It's around 0 degrees, it's around the equator, but it is now so big that it is, how big is it? It is, so I set this to 540.
Can you explain the difference between circle distortion and bearing distance? Like,
Okay, bearing distance is a parameter. It's right here. It's a parameter I created. And it's just a number between 0 and 10,800. It's just a way for me to control the point. It's a control. It's a dial for me to change, to illustrate how these things are working. So, let's set this back. So right here, we've got a circle that's centered here, and at 10,304 nautical miles, that circle's radius goes almost all the way to the equator, right? So that circle is something that's like about this.
so bearing distance is just like
The radius.
Metal radius. Okay.
It is the radius of the circle, but the trick, the mental difficulty of this, it's a circle sitting on the surface of a balloon, right? It's a circle. It's like you've taken a balloon and you've drawn a circle on the surface of a balloon. And then what the Mercator projection does is it takes that balloon and projects it onto a cylinder and then unwinds the cylinder until it's a flat sheet. And so that's why we end up with these weird distortions. If I make this circle big enough, it ends up, this circle is now so big that what it's done is it's gone through and come back outside the other side. And so it's actually, the whole of it is, what's happened is it's flipped. Remember I said that Tableau will pick the smallest area to color? This area here should have actually been colored, because that's the actual circle that I wanted, but it's, oh, no, it's doing it correctly. That's right, it's picking up the correct area. So what's happened is, opposite our circle, which is centered here, this is all the area that's not being colored, right? If I make this large enough, slowly these edges will move out until I end up creating a buffer around the whole planet. So I'll just click this, and you can see it just keeps getting bigger, little bits at a time, as this circle consumes the whole planet. So the main thing to be aware of, I'm going to set the circle size down to being something reasonable, is how circles get distorted as you, and I'm going to save this because this will break at some point. I'm going to set this to 1200, so it's 20 degrees at the equator. 1200. Here we go. Watch how the circle distorts as I move it further north. So I'm moving it north. See, it's getting bigger and bigger and distorting. And I'm going to save it right now because when I hit 70 degrees, it's going to crash. Or it should crash. So this circle here, when I hit 70 degrees, the circle is actually hitting the, oh, it's not crashing, good. What's happening now is I've got a circle that's just touching the North Pole. As I go past 70 degrees, it's now wrapping over the North Pole around the other side. And you can see this is still a circle on our planet, but because of the mapping projection, it's getting all distorted. All right, so on Thursday's class, what I'm going to show you is using that bearing file, which if you looked in it, it's just a list of numbers, right? And it's a list of, it's got one row per degree longitude. Yes. Well, no, it's got one row per degree of azimuth of direction. And I'm going to use that to, where did my average? I'm going to use that to create a map that illustrates the average extent of seasonal ice on each day in our data record. And then if we have time, I'm going to use that file. And if you look here, like I can, as I go through, you can see the seasons moving the ice up and down. And I'll go through the calculations for how we do that, but I'm going to upload this book as soon as class is over. I'm going to use that bearing file, and I'm going to show you how to, in the data sources, to link that bearing file into your data. And provided we can move through this pretty quickly, I'll show you how to take the hurricane data where they have the distances along the 4 quadrants, and we'll create kind of like an ellipsoid using those 4 distances, so that we can draw the size of the actual size of the hurricane on the map. And we only have about 3 years worth of data where they actually collected those distances, but we'll actually draw that on the map so that in the hurricane file, we'll see the actual size of the hurricane change on the map itself. And I think that'll take us up through all of like the most complicated aspects of, not the most complicated aspects, but all of the sort of foundational parts of working with geographic data inside of Tableau. Uh-oh. All right, I'm gonna let you guys go. Have a happy evening. It looks like the roads are cleared up, so it shouldn't be too bad getting home.